Integrated rate laws are another way we can handle chemical kinetics data. What's great about them is they quickly manifest the order of reaction with respect to a single reactant. We can use integral calculus to transform the graph of the data into a straight line for a particular order of reaction. That's what's done. We're using integral calculus to integrate the original rate law. And this will also produce the rate constant in the equation that is the form of the integrated rate law. I want to remind you that with the method of initial rates, we were trying to find the slope of the plot of concentration versus time early on in the reaction. And one of the challenges there was to line up the slope correctly with the initial slope. Plus, what's really going on in all of these graphs is that we're trying to figure out the rate of change of the rate, because we're trying to find out how the rate, which is the slope of the plot at any point, matches with the concentration of the reactant at that point. So, and remember that we were trying to find an exponent. What we were trying to find when we say order of reaction was an exponent to write on top of the above the concentration of a certain reactant in the rate law. And you couldn't derive that exponent. You couldn't just pull it as the coefficient from the overall balanced equation. It had to be experimentally determined. Well, how do we do this with integrated rate laws? First of all, let's see the various forms that are just provided to us on the AP chart. What you see in the blue box is something snipped from your AP formula or equation chart. And here's the meaning of those four things in that box. The first three are integrated rate laws for overall, for particular orders of reaction with respect to reactant A. The fourth thing there is the half-life equation, which only relates to one of those three integrated rate laws, which is something we're going to talk about later on in this video. How can we ascertain whether the reaction is zeroth, first, or second order with respect to a reactant? Well, we're going to do plot matching. We're going to prepare the plots as if, putting the data in as if we had zeroth and first and second order, and we're going to see which one of them comes out linear, and whichever one comes out linear, that's going to determine which one is the which order of reactant we have, with which order of reaction with respect to a particular reactant we have. Okay, so for zeroth order, the plot of concentration A versus time is linear. How do we get this? Well, the rate law is for a zeroth order is rate equals K. Notice there's no brackets, anything over here raised to some power, because the power was 0 and anything raised to the zeroth power is just 1. So this is the very simple rate law for reaction with respect to A when A is zeroth order. Well, just to expand on that, the rate is really the change in concentration of A over the change in time, which is final concentration of A minus initial concentration of A over time, and that's all equal to just a straight up constant. Well, when we integrate that rate law, here's what we get. At least this is the form that's given on the AP chart, and it's right. So how about for first order? The plot of natural log of concentration A versus time is linear. So how do we get that? Well, here's the rate law if the order of reaction with respect to A is 1. Our 1 is implied here. So expanding that rate law, we say again, rate is change in concentration of A over change in time. That's final concentration of A minus the initial concentration of A divided by the change in time. And here we have K times the concentration at a particular time raised to the first power. If we integrate that law, here's what we get, and this is what's posted on your AP formula chart for the first order integrated rate law. But it's not in the helpful slope-intercept form. So what does that look like? Again, the blue line is supposed to be the straight line that would be produced if this reaction was first order with respect to A, and we plotted the data according to this equation, plotting natural log of A on the Y and time on the X. And then again, y-intercept is the natural log of A original, and our slope, rise over the run, is still negative k. Because this is out a linear plot, we could figure out the rate constant k from the slope. And if it turned out linear, that's our evidence that this is first order of reaction with respect to A. So a second order plot plots 1 over A on the y-axis and t on the x-axis, and that gives a linear plot if the reaction really runs second order with respect to reactant A. Of course, the rate law, when we're talking about a second order of reaction with respect to A, has a square on the A in the rate law. Expanding that, we're saying the change in concentration of A over change in time, which is final concentration of A minus initial concentration of A over change in time, is equal to some rate constant times A at time t squared. Notice there's no negative on the k this time. The integrated rate law then is 1 over AT, so 1 over the concentration of A at a particular time t minus 1 over concentration of A original equals the rate constant times the time. What does that look like? Notice this is the only version of these three that has a positive slope. And again, it'll be linear if we plot the data with 1 over A on the y-axis and time on the x-axis. So y-intercept is going to be 1 over the concentration of A original. And the rise over the run, which is the slope, is going to be our rate constant k. And notice without flipping the sign, it is the rate constant k. If we get a linear plot when plotting the data as described here, our rate constant will simply be the slope of that linear plot. So I need to go over half-life. Half-life is a concept you've been familiarized with before, probably talked about in biology when you're talking about carbon-14 dating, stuff like that. The amount of time required for half of the original mass or original number of moles of a substance to be converted into another form. So we're talking about in a certain amount of time, half of it gets converted into a different form. And so only half of it is left now. No matter how much we started with, after that same amount of time, we keep getting half as much of the stuff remaining in its original form. So I already mentioned that, by the way, all radioactive decay processes follow first order kinetics. Okay, so this slide is about the concept of half-life only making sense for first order kinetics. I've written for you the 0th, the first, and the second order integrated rate laws. And I want to point out that we're looking, well, I'm going to rearrange these all to solve for time. So I want to point out that for 0th order, if I started with a concentration of 2 molar and ended up at a concentration, concentration of 2 molar and ended up with a concentration of 1 molar, I'd have negative 1 on the top, right? Divided by some constant, and that would give me my half-life, right? What if I started with a concentration of 4 molar and ended up with a concentration of 2 molar, so that's the time it took for half of it to be decomposed or altered into a new form, converted into a new form. Then instead of having 1 over negative k, negative 1 over negative k, I'd have negative 2 over negative k. What if I started with 1 molar here and ended up with half a molar there? That would still be the change, conversion of half of the original amount, but I'd end up with 0.5, negative 0.5 in the numerator divided by k. So you can see my time is not a fixed amount of time if I'm talking about 0th order of reaction. And let's go down to second order reaction. I'm going to deal with first order later. If I solve the second order integrated rate law for time, and I want to talk about the half-life, which is the time for half of something to be converted into a different form. If I started with 1 molar here and ended up with half molar here, I would have 1 over half, which is 2, minus 1 over 1, which is 1. So I'd have 2 minus 1. So I'd get 1 divided by k, which would be my half-life. But what if for that same exact reactant, I had started off, instead of starting off with 1 molar, I started off with 2 molar. Now this is a half, and I end up with 1 molar at a half-life, and so that's 1. So I'd have 1 minus a half, so I'd have 0.5 in the numerator over k, which is a different number, different amount of time. So you can see time is changing as the half-life time is changing for second order kinetics. So I hope I've established for you that 0th order and 2nd order kinetics don't produce a constant half-life. But let's talk about why 1st order kinetics, or how 1st order kinetics do. Okay, so here we have the equation that I had on the previous page for 1st order kinetics solving for time, integrated rate law for 1st order kinetics solving for time. Concentration, natural log of concentration of A at a particular time minus natural log concentration of A original divided by negative K. Well, according to the rules of logarithms, subtracting the difference between two logarithms is equal to the ratio of them. And so I've done that substitution here, and then I've done a little math rearrangement here. So if I have a half-life, if I'm talking about the time it takes for half of the substance to convert into another form, then this ratio stays fixed at a half. So if I started with 4 molar and ended with 2 molar, that's a half. If I started with 2 molar and ended with 1 molar, that's a half. If I started with 1 molar and ended up with half molar, that ratio is still a half. And so my natural log of a half is always a fixed value, which if you put in your calculator, you'll find out is negative 0.693. And then I just divide it by the negative of K, which is why your formula chart shows you that the half-life is 0.693 divided by the rate constant K for the reaction. But again, it only makes sense for 1st order kinetics.